Good afternoon, everyone. Thanks for joining us today for SME's Aerodef Manufacturing webinar, The New Frontier in Inspection Surface Intelligence. Today's webinar will cover the many challenges manufacturers struggle with surface inspection, including intermittent failures around cleaning, coating, welding, and bonding operations. You'll learn how these challenges affect supply chain, warranty, brand imaging, dissatisfied customers, and even frustrated employees. I'm Carl Mitroff, Conference Manager, and thanks for joining us today for today's webinar. We have an exciting topic to cover, but first, a few housekeeping items. Google Chrome is our preferred browser. Your microphones are automatically muted, so if you have any questions regarding the functionality, please use the chat feature. And if you have technical questions you'd like to ask any of our presenters this afternoon, you can submit them using the Q&A box. We'll be monitoring both. Moderating today's webinar is Lou Dorworth, Direct Services Manager at Iberis Training. Mr. Dorworth has been working in the advanced composite industry since 1978. His background includes over 40 years experience with composite material research and development, manufacturing engineering, material and process engineering, tool design, tool fabrication, and of course, teaching composite-related topics. Lou is highly engaged in the composites industry, volunteering his time in many professional associations, including SME, as an Aerodef conference advisor and a recent past chair of the SME technical community. Joining Lou this afternoon is Lucas Dillingham, Sales Manager with Brighton Science. Please welcome both Lou and Lucas to today's webinar.
Thank you, Carl, and good afternoon to our attendees. Welcome to our webinar. As Carl mentioned, my name is Lou Dorworth, and I'll be moderating today's event and fielding questions from you. So please type any questions you may have in the QA box as we go along, and we'll answer them during the webinar or at the end of our QA session. Today's speaker is Lucas Dillingham. Mr. Dillingham is the sales manager at Brighton Science and is responsible for all global sales. He has over 15 years of materials science experience, helping a variety of organizations create specifications, set up workflows, advise on surface preparation techniques, discover non-obvious variables causing lost time, material, and undue warranty costs. Lucas currently leads the Brighton Science sales team, delivering surface intelligence to manufacturing organizations around the world. With that, let's get on to the webinar. Lucas, it's all yours.
Thanks, Lou. Appreciate it. Everybody joining, thank you again for taking an hour out of your day, whenever that might be. And thanks for joining in the future if you're listening to a recorded version of this. Really appreciate your time and attention. So with that, let's get right into it. All right. Why are we here today? Why are we gathered here today? It's not a wedding or a funeral. We're trying to learn a little bit more about surfaces and how do we get a lot better at designing, developing, scaling, controlling, troubleshooting, things that have to go together using things like adhesives, sealants, coatings, paints, things like that, right? And the state of the union today really is that manufacturers across industries really struggle with intermittent failure around these particular processes, or they may not have the confidence to switch from traditional fastening to structural adhesives, right? Or they may not take advantage of the latest advances in lightweight materials or high performance coatings because there's a lack of confidence in being able to do these processes in the way that the market and the final customer really demands them to be done, which is something with really very high reliability and very high predictability, right? These things today really carry risks associated with warranty, damage to brand image, and really dissatisfied customers and frustrated employees. So, having been out there in the marketplace for the last decade or so, talking with people, solving these problems, we've really learned and heard a few, I'll just say, archetypes, right? Basically a couple themes really present themselves over and over. Companies strategically are really focused on creating a culture of continuous improvement, right? Benchmarking to learn from failures and successes across programs and locations. all right, hey, on the last program, we did it that way. That was a nightmare. We got through it, but it really wasn't very fun. How do we get better for the next one? Or the flip side, which happens a lot, hey, it worked great last time. Why change anything? Let's do it the same way this time. Competition, right? Competition is getting more intense, really, no matter what industry you're a part of. As we have kind of a more globalized economy, though I guess in recent years, maybe a little bit less, but in general, more globalized economy, there's competition coming from all over the place on creating high performance products. And most of us are really, we care about presenting a premium brand image to the world for the space that we inhabit. And these are themes that no matter if you're doing plating for an aerospace component or you're building a cell phone, all of these are in your orbit to some degree, right? On top of that, there's really specific issues that all manufacturers are trying to continually address. One of them is to reduce the rate of failure, right? We do not want failure at the rate that has occurred in previous programs, years, jobs, whatever it is. We really want to improve internal knowledge around processes and material fundamentals. I hear a lot of people talking about these days, especially during COVID. I don't know if I could say post-COVID, whatever that is, whatever's happening right now, where there's been massive brain drain in a lot of organizations on how to put these advanced materials together. And so people are leaning more on the vendors of, say, adhesives or the raw material. And thirdly, everyone is looking to get better control over the manufacturing process, right? As labor is a major challenge, I mean, from straight hiring to even just getting people to really do the job in a conscientious way or exercise some critical thinking, we got to have better control, right? You'll see people going to automation as one way to get that. It's not just a cost thing, it's a control thing. But you'll see a lot of people looking at trying to get more data. We need more information more easily in more places to be able to do this successfully. So we've got a poll here. We're going to rank our objectives on kind of what we're working on internally. And I think Carl's going to be able to fire that poll up for us, and we'll take 60 seconds or so to answer it. So we've got kind of three here. Which of the following objectives are your top priority? 1, reducing the rate of failure. 2, improving process and materials knowledge internally. Number 3, control and gain efficiencies in your manufacturing process, right? Are you implementing lean principles and trying to get up to a better CPK value, right? Or you just simply, do you want to just sleep better at night because you know that bond is going to hold after it's left your factory? We'll give this a couple more seconds and then we can keep moving. All right. There we go. Okay. Improved process and materials knowledge is a clear winner. 77% of the respondents. And honestly, makes sense for a webinar, right? We're here to learn. And yeah, makes total sense. So, all right. So let's take a closer look at what's going on and what's possible. All right. So it is a race to the future, right? Manufacturers, we got to create a pipeline of innovative, high-performing products. They got to be easy to assemble, right? We don't want nuts and bolts. We want to use adhesives, right? But working with these new materials in a global environment, it's surfacing a real supply chain crunch. I mean, if you used to get your substrate material from vendor A, but now all of a sudden you're being told, hey, we can't get that anymore, sorry, or we've had to change something fundamental in the material, you're sitting here saying, do I need to requalify? Can I use that in the same way? Is it going to do the same thing, right? And that all flows down to production challenges. So we've got to get better. We've got to get smarter. This manifests itself in some very real world spinouts, right? Your smartwatch screen pops off, your newly refinished wheels bubble and don't work anymore. The coating on your medical tube or catheter starts bubbling and peeling off, right? This is real. And when this occurs, the Twitterverse is not very kind, right? the forum warriors, the keyboard warriors go crazy. So even if you have a super small percentage of failure in your overall production run, guess what? That makes it to really a pretty unforgiving audience out there in the real world. And it's not necessarily fair to the manufacturer, but it is the world that we live in, right? So guys go crazy on the forums. Hey, my cell phone screen fell off. It's no good. Or I just bought my new Ford Bronco and I've got this tiny little chip in one corner, and this is crazy. I just spent 80 grand on this thing and Ford couldn't even ship it to me on time. Like, what the heck? So this is what we've got to deal with. This is that brand image problem, which can be pretty damaging. So in each of these high profile cases, right, the issue really isn't a design flaw. It's not that we don't have our bead width of our adhesive thick enough. It's not that the way that we've designed the joint so that the load path is going in a specific direction is incorrect. It's a bonding problem or adhesion failure. It's some failure in the surface where the surface is different than we wanted it to be at the point in time that we put our coating or sealant in contact with it. In fact, about 90% of all the adhesion failure issues that we see out there in the world are related to surface problems. All right, and it's not just, hey, we didn't get it clean enough today, or the prep was wrong. There's a human and organizational factor at play. We've made a slight change at the supplier and how we're packaging these, or they sat a little bit longer in the truck, so there's a different environmental condition going on. Right? There's various points in the way that we've designed that workflow where things can change with surfaces, which can put us in really a compromising position. So these failures, what do? They lead to scrap and rework expenses. They lead to warranty claims. They lead to reputational damage. And then what happens is process engineering or quality engineering, sometimes development, are now running around trying to figure out where is the cause of this failure and how do I implement a corrective action. And not only that, say I'm the manufacturing engineer or the process engineer, I now have to create a large report that I've got to spend, weeks on to deliver to management on what the problem is and what the fix is and how much it's going to cost to fix it. All right, it's a big time suck away from doing the work that we're supposed to be doing, regardless of our function. Getting to responsibility can be difficult, right? Who is actually responsible? Is it the vendor? Is it the shipping company? Is it the receiving guys in shipping that left it sit on the dock during winter? Who owns this problem, right? We want to avoid finger pointing situations like this. All right, so the visibility to the issue for surface chemistry, plus the experience to know what to do with that information, is what we call surface intelligence. All right. There are new tools available, there's new analytical capabilities, and there is expertise available that can give us insight, can give us the ability to monitor and analyze these variables in real time. It can give us the ability to increase control over our processes. It gives us a common language to talk about critical adhesion issues across the organization, which we find to be a major barrier, especially if you've got a globalized supply chain. And then not the ability to not just diagnose and fix them, but actually prevent these problems from happening in the first place, right? Which really starts in the development side. So let's see what this looks like in action. So what's really important is to think about is we've got three key inputs to a reliable coating, sealing application, or bonding application. All right, it's the chemistry we're applying to the surface. Is it correct? Usually the Henkels of the world, the Solvays, they do a very good job controlling monomer ratios, and they're not shipping out bad batches of adhesive or coating too often, right? Almost never. We have to control, the second input is how we're going to apply that chemistry to our substrate. The cure profile, the environmental conditions, the fixturing, the pressure, right? There's a lot of physical and mechanical things there that need to be aligned. The third thing is the substrate that we are going to apply that coating to. Do we have the right surface chemistry to play well with what we're putting together? So if we do those three things, we're going to get a reliable and repeatable output 99.999% of the time. It is going to work as designed, right? So that's very important. Manufacturers do 2 out of 3 pretty darn well. The Henkels and the Solvays of the world do a great job controlling the product that they're delivering. We do all kinds of monitoring around fixturing and environmental conditions for when we're actually applying that. Cameras behind robotically deployed sealant to make sure that bead width and color is correct, right? Mixture nozzles, I mean, all kinds of stuff. But we're not really tackling surfaces. And so when we look at surface management by design, there's 3 things we got to get right? How do we tackle that surface piece? We got to define the surface we need in terms of surface chemistry. All right, we got to define how we're going to create that surface, and then how are we going to maintain it, right? So that gets to how are we going to work with it? Are we going to clean it? Are we going to treat it? Are we going to grit blast it? Are we going to laser it? Am I going to just wipe it with acetone? And then how am I going to deal with it end to end? All right, I mold it, I pack it, I ship it, I unbox it. Then what? Who's going to handle the cleaning? Usually people don't look at cleaning or prep as value add, but it's a key step. All right. And then thirdly, how are we going to monitor to consistently keep that surface as designed, right? Surfaces are sensitive, they are variable, and we're going to get into this, here in the next slide or two. How do we keep it that way? So we got to be able to solve for the problem if it occurs. We want to prevent it from happening in the first place, and we got to have a good control plan in place. So let's get into some of the chemistry here and what's going on with these surfaces as a whole. So, what is a surface? We've got to define what is a surface for these applications, right? A surface for a bonding or sealing or coating application is basically the top 2 to 10 or 20 molecular layers, okay, on a given material. If I can see a fingerprint on that surface, that's like 10,000 molecules thick, all right? The region that we care about is totally invisible to the eye. All right, what we're showing here in this diagram, just using metal as an example here, when I create a metal surface, say through machining or abrasion or laser ablation, I've fractured molecular bonds. I've literally ripped some portion of the bulk material apart, and now I've got all these reactive sites. Within milliseconds, I get an oxide layer that forms, I get some water vapor that gets on there, and then eventually I start getting some contamination, some adsorption from the environment or from handling, usually in the form of hydrocarbons, right? Every time a molecule comes in touch with that super fresh surface, you lose some of that reactivity. You lose a reactive site, literally used up. You got nothing to work with there. The jargon that you'll hear as you go out and research, right, around this is the term surface energy, right? And surface energy just simply it's a phrase that describes the total amount of chemical reactivity that's present on a surface within, at a given point in time. Certain materials natively have more surface energy than others, depending on their chemical makeup. Crystalline materials, glasses, ceramics, metals, they tend to have a lot more energy. That also has to do with specifically what they're made up of than, say, polymers. Right? And polymers follow a little bit different scenario. So every material goes through this decay curve. All right, I've got surface energy on the y-axis as a function of the elapsed time from surface creation on the x-axis. When I create that fresh surface, and if it's a polymer, it's typically through surface treatment. If it's a metal, it's typically through cleaning or abrasion or something like this. I'm going to start with a relatively high energy level. It's going to immediately start to decay, right? And at some point, it decays so much that you don't have much there to work with. You don't have much reactivity for your adhesive or your paint to even appropriately wet the surface, right? Where that is, system dependent. How fast this happens, it's material and environment and system dependent. That's the answer for everything. Every engineering answer is it depends to every question. So, but this is it's very important to understand, where are we on this scale? Where do we need to be, right? This gives us a baseline to function from. When does my system work? When does it start to kind of get iffy? When does it start failing completely? So let's take a look at polymers here. When I'm creating a polymer surface, it's pretty different, okay? If I've got a bulk polymer that I pull apart, right, I get essentially 2 things can happen. I get some chain scission, or I can get chain pullout, all right? But there's fewer broken bonds. There's low chemical potential, right? Low reactivity on these surfaces. they don't have much reaction to the environment. All right, they're fairly stable, right? But to be able to do something with them, we typically have to do surface treatment, right? Could be a plasma, could be a flame treatment, could be a corona treatment. Sometimes there will be primers, right, that we'll use to help try to do this. All right. They also have high molecular mobility, right? So substances can really diffuse from the bulk up to the surface, like low molecular weight material can be a real problem. Uh, and that actually can be a real killer that we'll see a lot in say, molding operations or film operations. So it's a little bit different setup, right? The surfaces of these things basically look like spaghetti. There's not a whole lot to work with there unless you do something to it. The decay function here looks a little bit different because you're starting from a lower surface energy to start with. You surface treat, typically. That increases its surface energy. And then again, it decays, right, over some period of time.
Lucas, can you discuss thermoset polymers compared to thermoplastics? Thermoplastics are much lower surface free energy, so we're dealing with something that's slightly
Yes.
more than that.
Yes.
But still much lower than any metal.
Yeah, much lower than any metal. So great question, Lou. Probably one of the better questions I've ever gotten on a webinar. So like take like an epoxy composite, like an epoxy-based composite, for example. They're actually in the polymer family, they're more crystalline. So when you go to abrade the thing, you actually end up you do get some molecular breakup of the surface. So like if you abrade an epoxy-based composite, for example, you'll see its surface energy increase through abrasion. Whereas if I've got like, something that's nylon based, you won't see that necessarily. Does that make sense? Does that help?
Excellent. Thank you.
Yeah, great. The other thing that you do need to worry about with treatment is you can create reactive sites on the surface, but they can reorient down into the bulk. Now, to Lou's point, that's thermoplastic really related specifically. But it's something to keep in mind, right? These things, the point here is that they're sensitive. It's a super thin region and it's mobile. Like things are changing all the time, right? So a surface that we care about for these applications is quite thin. It's invisible to the naked eye. Surface energy gives us a way to start describing kind of how these things move around or how they change as we do preparation to them or cleaning. But how do we really measure them? All right. Well, traditionally, we've got a couple techniques, right? We've got FTIR, all right? We've got vacuum techniques like XPS, X-ray photoelectron spectroscopy. We can do some chemical residue analysis, all right, through like say solvent extraction. We can do wetting methods like contact angles, and we can do surface roughness analysis. Now, a lot of people do roughness like post-prep because the common wisdom is we need to roughen surfaces to get good bonding. Tells us nothing about surface chemistry, simply tells us if we hopefully got the surface a little bit rougher. It can be important, usually a secondary effect for bonding, not a primary effect. The challenge with some of these, of course, is that things like FTIR and XPS, they're laboratory techniques. We can't deploy them out in the field, right? They're not, and you need to have a really trained operator to be able to use them. You can get great information out of them, but not super practical on a day-to-day basis. So we've got another poll here. How are you guys measuring surface chemistry today? Got about 60 seconds on this. So do you guys have access to FTIR? Is there an XPS around that you get access to? Contact angle, chemical residue, surface roughness, or are you not measuring at all? And how is that working? We'll keep this up here for the next 30 seconds. Keep it moving. All right. Okay, we got 4 votes for chemical residue, 0 for XPS, One vote here for FTIR and a few for we don't measure. Good. Thanks everybody for answering that. Okay, a couple things to consider with some of these measurement techniques. All right, the FTIR technique matters. Okay, most people that have access to FTIR are doing ATR. All right, it can be good. It's good for compound identification, but the problem with ATR is you're sampling down in the bulk material, like a micron or two. So it's actually not telling you, if you guys remember, we really care about the top 1 to 15 to 20 molecular layers of that surface. ATR sampling too deep. You can use grazing angle spectroscopy, but you need a reflective plate. So it requires you to be able to basically wash a part off in solvent, collect it on a reflective plate, and then you can get real thin film analysis on what's there. So can be great, can be quick, not always the way to do it. Almost everyone's trying to do ATR, but it's not really even sampling the region that you care about. Another thing is SEM. A lot of people have access to SEM. You get these incredible images. I don't know if folks here have ever seen like those insane images of like an ant head that are like black and white or green, where you could see the individual hair individual hairs on an ant head. Those are done in SEM. It's always awesome. A lot of SEMs now, they've got an EDX attachment, which can give you bulk elemental composition. But again, you're getting like 2 microns down into the surface. You're ignoring that whole that actual region that you care about a lot. And so many times when we've gotten into troubleshooting situations on adhesion production challenges, many times the engineering team will say, well, we tried ADX, but we didn't see it. We couldn't see anything. We couldn't distinguish. It just looked like aluminum. We couldn't see anything. And that's because we were getting down, too deep. And then, of course, profilometry is just not suitable for surface chemistry. So it's not going to tell us anything about what's going on with that surface, really, from a chemical perspective. So let's talk wetting measurements. All right, these are the most deployable in manufacturing. They're literally the easiest to use. Traditionally, you'll see dyne tests done a lot in, I'll just say, polymer processing, like film processing, molding. Dynes have been around forever. Inks have different surface tensions. You paint them on the surface and you count to 5 and watch if they beat up or wet out a little bit. And you try to get an indication of what's the surface energy of the part. Water break check, basically the most ubiquitous way for the aerospace industry to try to understand if they've got clean metal parts prior to PAA. Prior to a lot of different things, but many times prior to coating or metal bonding. Very much a binary, go, no go. Usually usually the company's relying on maybe someone named Todd and someone else named Sarah who've been doing it for 35 years and they trust them. So it's certainly subjective and certainly not 21st century solutions. And then more and more people now, of course, are starting to use water contact angle because this is a way to get to a quantified water break, which allows you to get a lot more accuracy, sensitivity, flexibility, and gives you data, gives you something I can port into a computer and I can start graphing, right? So it's just absolutely the way to start looking at it. So let's look at some of these deployed. So typically, surprise, surprise, we do make some of these. This is one of the things we do. They come in handheld versions. They come in automated versions. We won't spend any time on this at all, but we will get into the data next. All right, so why do we like the water contact angle technique? All right, one, it's sensitive. It is as sensitive as XPS. All right, it's literally the most surface sensitive technique available today that I can just deploy on anything, anywhere, just in atmosphere. All right, as an example, here we've got some nickel alloy that's dirty. All right, it's going through a stamping process. It's dirty. The manufacturer here is trying to evaluate, I need a new way to clean this that's environmentally friendly. How do I know that this new solvent package is going to work for me? All right, and we basically can get to a very objective measurement of metal cleanliness here by creating a carbon and nickel ratio in our XPS system, and we can correlate that directly to a water contact angle result. All right, and that carbon and nickel ratio is just basically how much carbon are we seeing in relation, how much carbon signal are we getting in relation to nickel on that surface. And you can see when I'm at an 80-degree contact angle on the right-hand side of the chart, I've got a very high carbon to nickel ratio. As I start cleaning this nickel through different techniques, my contact angle goes down, 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 and down, and my carbon to nickel ratio goes down. I mean, it's a pretty darn close to a 45-degree line, right? It doesn't get much better than that. So one of the reasons we like this water contact angle method is that it's sensitive. It's accurate, right? It tells us when our surface is changing, which is really nice. It's not just for metals, though, as we'll see here in this next slide. You can go one forward, Ricky. Sorry. As you'll see here in this slide here, we can map our contact angle on the y-axis as a function of the atomic percent oxygen that we're putting onto this polyethylene through plasma treatment. Very similar curve shape, right? So we get this in 2 seconds, and it's super sensitive and it's super accurate, and anybody can do it. So it's a very nice thing. When we start putting this to practice in 2 ways, right? One of the things that we look at is what's its sensitivity to contamination, as well as how do we correlate this, or how do we correlate our surface chemistry, our surface condition, to bond performance, right? To fundamental performance of the joint. And we end up getting charts like this, right? Which give us a lot of confidence in the fact that if we design our process well to create a particular surface chemistry, part after part, shift after shift, operator after operator, that gives us a very specific water contact angle band that any movement in that band can alert us to when things are moving out of spec. Just like we would put a torque specification on a fastener, we can put a specification on surface chemistry for the factory. All right. On the left-hand chart, we're showing the technique sensitivity to silicone, right? Silicone, probably the worst contaminant that you could have, floating around in a manufacturing facility that's doing bonding or painting or sealing. It's insidious. It's everywhere. All right. It's in your lotions. It's on people wearing, I guess not many people wearing Livestrong bracelets anymore, but it's in your Apple Watch band. I mean, it's all over the place. It's people buy silicone gloves, walk into the plant and open up the box on accident. And all of a sudden now you got silicone floating around. The chart here on the left shows we've got our water contact angle on the left axis, the amount of silicone that we're applying to composite samples on the bottom axis, and then the atomic percent silicone on the right axis. And so what you can see here is once we get to 10 micrograms per square centimeter, we're up above 40 degrees. Typically, when we see real problems with adhesion in most applications, it's when you're in this kind of 30 to 40 micrograms per centimeter, and you're right in that kind of 80-degree water contact angle range. That's an immediate flag, right? Like if we go out and we're doing some problem solving and we see an 80-degree surface and there's been some intermittent failure, time out. Let's take a deeper look at that. On the right hand, yeah, go ahead, Lou.
I was just going to chime in there. What do you see in the field normally, especially with free coat 44 molding composite parts with thermosets and whatever fibers, as far as the transfer of silicone from the free coat 44, depending upon, I guess, many factors in manufacturing?
Lou, last, I did a webinar from Composites World where I talked about, mold release and transfer mold release, and it actually got some people a little bit concerned because of the way that I'd said that. Nowadays, right, if people are using hard coats and they're using the products as designed, as described, like if it's a moisture cure product, making sure you have enough moisture in the environment, making sure you're giving enough time to cure. Once it hard coats on there, it's pretty good. Like the products themselves are actually quite good. What happens, what we see is essentially operators either not following the instructions to a T or not taking into account all the variables that can cause that stuff to not cure fully, cause it to transfer to areas of the part that you don't want it to go, or to just mold too many parts without reapplying, and then they wreck the tool. One of the things that we've found, of course, is that transfer is a lot more common than you think. Again, not usually a mold release problem, more of an application problem. It's way more common than you think. I mean, I've had multiple experiences where we found release agent on the backside of composites, and engineers just look at us like we're crazy. Like that's not possible. It's not supposed to happen. Absolutely happens. Um, I would the way that I would answer that, Lou, is the where and the how is usually more important than the what, if that
Yeah,
makes sense.
if we can identify the what, we can go back and fix the where and the how.
Right.
Uh,
Yeah,
yeah.
exactly. And I mean, we're using free code, we're calling out free code 44 here just because this is what we used in the experiment because it's easy to apply for the experiment. Um, it just made, because in this case, we're just trying to understand, hey, what's the sensitivity of the technique to contamination? And what's the contaminant that we really care the most about? Well, it's actually usually not hydrocarbon based contaminants. It's almost always silicones. Now, every application is different. If I'm doing precision machining and cleaning of a medical implantable device, I also care about hydrocarbons, and I'm looking at a whole different level of clean. Um, yeah, that's how I would answer that
All
problem.
right. Thanks, Lucas. It follows along with our observations.
Okay, great. On the right hand side here, we've got a chart where we're taking these samples and we're correlating the bond performance. All right, our contact angle's on the bottom axis. Okay. On the left axis, we've got fracture toughness. And then on the right axis, we've got percent interfacial failure. All right. I saw Doug Decker was here listening today. He's seen this chart before, and it's a really good one, right? Because what happens is that as we add contaminant to that surface and as our surface energy decreases and our contact angle increases, what we see our fracture toughness decrease here. Now you can't see my cursor. From left to right, that's the top curve. Fracture toughness decreases, and the percent interfacial failure increases, and there's an inflection point right at about 50 degrees in contact angle. So below 50, things are working pretty well in general, though you can see kind of at the 40s things start changing. Above 50, things really start falling apart. And this is pretty common for a lot of applications. The range will be slightly different, maybe that cutoff point is a little bit different, but really, really good rule of thumb. If you're familiar with water break testing, above 60 degrees, water break always fails. Below 40 degrees, water break always passes. 40 to 60, sometimes it passes, sometimes it fails. Just doesn't really have the accuracy to give you that kind of gray zone. That gray zone is super important, right? Because that's usually what's happening in processes is you're operating in this gray zone. And that's why once in a while things fall apart and nobody can figure out why. Go to the next slide, Ricky. We're going to be able to quickly screen technology options, right? What solvent package? Am I using plasma? Am I using a Scotch-Brite? Am I using a 220 grit? If I use a 220 grit paper, can they get anything from Home Depot, or do I need to actually specify what paper they're going to use? I won't spoil the answer of that one. And finally, the thing that we get really excited about, because this gets us to our prevention piece, is providing a data stream, right? Considering this is aerodef, and let's make an assumption that some of our attendees are in the aerospace industry. When we talk about digital thread, talk about digital twin, right? This is where that comes to practice. This is where it comes to life. We get a data stream in the factory at the point of application for what's going on with our surfaces, right? Here's an example of an automotive manufacturer making a computer. They've got an environmental seal that's super important, and they're trying to set up a process that's reliable. So each one of these boxes represents a part, 1 through 10. We've written the word component here. I've got water contact angle on the left axis, and we got 3 process steps. We've got the incoming material that we measure from the supplier. We've got an alcohol wipe to help normalize that surface, and then we do a plasma treatment. These are not the only tools in the toolkit for surface prep. This is just what made sense for this particular manufacturer. And what you can see, just quickly scanning left to right, is our incoming material in general is right around 60 degrees. The IPA wipe brings it down about 5 degrees or so, 5 to 10 degrees, okay? And the plasma, on average, gets us to the mid-20s. right? But there's a couple interesting things here. Component number 3 and component number 4, the incoming material was super different. It had dynamic wetting all over these cast aluminum parts. The rinse process that they were using had gone to heck, and it wasn't working anymore. But our alcohol wipe returns us back to the 50s, and our plasma gets us back down to the mid-20s. Our process handled that incoming variability without an issue. Great. If we go to component 8 and 9, though, and you look at the circles around the purple dots, our post-plasma measurements are showing us in the 40s, right? It's like a 39 and a 45. Totally different. What happened? We go and investigate. An operator had selected the wrong robot program, which was moving that plasma jet farther away from the surface. So we were able to flag that before those parts were fully assembled and shipped out to the customer for reliability testing, on your favorite new electric Mercedes or, whatever it is you're buying. So here we get to, not only do we get to being able to quickly scale a process that is doing things to the surface that are invisible to the eye, we get a more reliable assembly. We're solving a problem super quickly that would have gone undetected otherwise. And we get a critical data stream that's alerting, or in this case, our advanced manufacturing engineers, that this is happening before it becomes a much bigger problem. So we're going to tell two stories, all right? And then we're going to start wrapping this up. So a way that people are putting this kind of data to practice, the surface intelligence to practice, all right? One of them, enabling a process development team to really overachieve deadlines. Okay, here we've got an automotive manufacturer. We're developing a new electric vehicle. We had 4 months to select a cleaning process for wire bonding of the battery module. And wire bonding is very sensitive to metal cleanliness, so we've got to get something that's repeatable. Also, if anyone here has looked at like a Tesla battery pack, it's almost impossible to avoid these days. What's it look like? It looks like basically an array of double A's. And they got to do wire bonding to each cell, right? That's got to be legit. So we worked with them to quickly select methods, test, develop a spec, and then provide test results to correlate to what they wanted to ultimately select, which in this case was a plasma cleaning step, highly automatable, good for this kind of application. All right, so in half the allocated time, we were able to nail the process and say, boom, this is what we're using. Here's the spec. Hey, manufacturing team, go ahead and start procurement. We can get moving. So took that 4-month project, took it down to 2 because we had that visibility and that experience on what we needed for the surface. This is one I like, near and dear to my heart, right? Mitigating risk and changing human behavior with surface intelligence. This human behavior angle is so key. And anyone who's been around for a while knows how hard it is. They could probably count on one hand how many times it's been done successfully, and they could probably count on all their fingers and toes how many times it's been done unsuccessfully, if not more. The human behavior thing is super important, but we don't get to change that without data and visibility as to what's going on. So here the challenge was that we had higher scrap rates on third shift. So we had increased failure down the line and at the customer. It was a problem. They were like, what's going on? And, everybody's first reaction is, oh, it's third shift. They're the early union folks, like they're brand new. They don't know what's happening. We can't really do anything about this. What we did in this case is we went and started gathering data in the cleaning procedures during every shift, first, second, and third, to see what was happening, right? And what do we find? Third shift was deviating from the prescribed standard operating procedure. They were reaching for a different cleaner instead of the prescribed one. It was out there on the cart. It was available. It wasn't what they were supposed to use, but it's what they were using. So we discovered that after a week. And what we did is we helped update the certification process. So we included some validation so that operators had to self-validate how they were doing the procedure. We also implemented better training and measurement for people coming into the factory, right, as they're having, like many people, a lot of labor turnover. And this really eliminated the discrepancy between operators, right? Christine was doing the exact same job as Jim now, no matter if it was first shift or third shift, right? Cleaning to a number. So this eliminated employee-induced spikes in scrap because we could use real data, right, to do this. So surface intelligence, what's it allowing companies to do? solve issues very, very quickly, right? Upstream contaminants, non-optimized parameters in your preparation methods for a primer application. It enables a supplier to meet whatever your cleanliness standards are from the OEM. So it just basically, we aren't operating in the world of mutual mystification. We've got a number that we got to hit, and we got a common language that we can deal with. There's prevention, right? We get to educate and train users on materials, cleaning, uses, right? We get to predictable models for adhesion success. Hey, if we get these three inputs right, how confident are we it's going to work the way it's designed? We also get to develop SOPs for workflow and processes, which is one way we get to prevention. Okay. Then there's the control piece, right? That digital thread, that digital twin. All right. It gives us a dashboard to show quality managers or process engineers how processes are in control. We can do reporting, right? Either to other teams internally or up and down the supply chain as needed. Okay. We can actually identify opportunities for training based on those dashboards, right? Just like we have many KPIs that measure different business functions or different role functions, we now get to apply that same methodology to something that has heretofore been completely invisible. All right. We also get trends for benchmarking. We now can get trend analysis data on how this stuff functions over time, right? Which is a great thing. So we can either compare from the early program to the later program, or we can always be looking at, man, this particular site, in California or wherever it is, not picking on California, but wherever it is always a couple percentage points higher. Like, what are they doing different? They're supposed to be doing the same thing we are. Let's go. There's an opportunity to fix something. Let's go check it out. Managing surfaces from supply chain to shipment is important, right? We call them critical control points. We've got the incoming material, we've got the storage and inventory, we've got the way we're going to clean it, we've got whether or not we're going to surface activate, and then we got the application of our sealant, coating, adhesive, etc. All right. We don't always measure all of these. We measure it where it matters, but having a baseline data set for figuring out, okay, what are these supposed to be, allows us to really rapidly cover problems if we encounter them. We talked a little bit about designing surface management into the entire product development process or product life cycle. All right. There are various areas where applying surface intelligence really matters, right? From product design all the way through process optimization, maintenance optimization, and yield optimization, right? We want to be able to make sure that a program that we launch is not only going to be on cost, on spec, and on time, but have the utmost quality possible. All right, the race to the future is on, right? It's time to take the lead with this. We can start eliminating these failures that we were talking about from our lives. They don't have to happen, right? The Fitbit watch is not a problem. The Google phone is not a problem. The medical catheter coating is not a problem. Or say if we were to look at the transportation industries, these start going away, right? These are all just the stuff that today, every week, we get a new little headline around a delayed launch or recall or something like this. These are really truly preventable through the application of a surface intelligence methodology. So let's see it in action. We got a quick video here, super fast demonstration. At least of the surface analyst. You're going to have to avoid the evil twin. Pay no attention to the evil twin with the quarantine here. But what we're doing here, and I'm going to narrate because it's going to be silent for those here on the webinar. We're measuring a piece of aluminum before. We get a 78-degree contact angle. That means that water droplet is really beating up, not very attracted to the surface. It's more attracted to itself. We just take a little piece of Scotch-Brite, right? This is obviously just a funky scrap piece of aluminum. We take a piece of Scotch-Brite. We take a measurement on that surface after we Scotch-Brited it. We get a 23-degree contact angle. So we've gone from 78 degrees to 23 degrees. Super simplistic demo, but gives you guys the idea of just how quickly I can now validate and put a number to what I've done to that surface. And that concludes our webinar. We've got exactly 10 minutes for Q&A. So I think we will open it up.
Great, Lucas. Thank you. That was very enlightening. Lucas's contact information is up on the screen. If you find that you have further questions after today's webinar, you can contact him directly. We do have a few questions in queue, and one of the questions is about the water itself. Water is a universal solvent. How clean does the water need to be in your testing?
Great question. So, we do want to normalize for water quality, right? So we would call it a probe fluid or inspection fluid. We use HPLC water. So that stands for high pressure liquid chromatography. We get it actually from a laboratory supply outfit and do some irradiation to it. So it's as pure as it can possibly get. We want to strip it of all minerals. We want to make sure its surface tension stays consistent. So we provide the water, regardless of whether it's an automated system or an inline system. We provide the water in a cartridge of various sizes.
Great. Next question is, how would you use the water contact angle method on a polymer surface that when molded is dry but quickly absorbs moisture from the air and it needs to be bonded?
Yeah, so if the surface is dry, like when you pull it out of the tool, for example, you can take measurements on it right away. If the polymer then begins absorbing moisture, if it absorbs it down into the bulk, you're not going to see that come up necessarily in a surface energy measurement or water contact angle measurement because it's in the bulk of the material, not at the surface of the material. I know moisture absorption is something we got to be mindful of in a lot of composite work, but it's not something that is going to affect surface energy a whole lot, and so it's not going to be something that a water contact angle technique is probably going to be super useful to get after. You would do something different.
Great. Is the water million ohm water?
I'm going to say maybe. David, I see your question. I actually don't know. I'd have to. Full disclosure, we buy the HPLC water from a laboratory vendor. I could look at the TDS. There is actually, if I'm recalling it now, there is something about its resistance rating on there, but yeah, I'd have to look. I don't know off the top of my head.
Going back to the water break method, which I find that the surface analyst is a good replacement for that. We see that sometimes there's a knockdown on the surface energy value when either solvents or water break tests have been done in process. Comparing that to testing with a surface analyst, for instance, can you share the benefit? For one, we know that you're going to have less water and fewer sites where water is present in the inspection if you do a grid. And what it would be the recommended grid to really get a good feel for the surface?
Yeah. No. So there's a couple questions wrapped up into that, I think, Lou. But
yeah.
We can talk sampling frequency first. So this is a spot check, and you're really evaluating what's going on based on statistics. So you do want to set a sampling frequency. How often and where you measure depends on how consistent your surface is from the get-go, right? If you've got a process that creates more variable surface chemistry, you want to sample more than if you've got a process that has very uniform surface chemistry. Typically, when we're doing that at the beginning of a startup, we do grid out a material and we measure in a grid to basically almost heat map it to get an understanding of what it looks like. Usually, there's a whole process we'll go through for this. Usually, you're taking a few hundred measurements at the beginning, and contact angle data will always fall in a normalized distribution. So you do it. Really, it's pretty simple. You do essentially a t-test. Figure out how many you want to, how many measurements are going to give you 95 or 98% confidence, depending on what you're comfortable with. That's one piece. So you do want to establish sampling frequency, and you want to make decisions based on the statistics. There's two things that we're typically looking at. One, is there a change in average, either up or down, because that tells you you're doing something. But the other thing is there a change in the standard deviation? If my variability is going up over time, that's a problem. That's something we want to avoid. If I do a process and my variability goes down, it shrinks, that's a good thing, right? If I clean the part and my variability shrinks, it says, hey, that's awesome. A lot of times when we're looking at like hand solvent wiping, you won't see a huge change in the average number, because say you're using alcohol. It's really a pretty benign solvent, doesn't really do a whole lot except remove fingerprints essentially. You won't see a huge change in the average water contact angle value, but what you'll see is a big reduction in the standard deviation.
Yeah.
Because you've normalized that surface. When we're looking at water break, one of the big advantages we found is, say you're using water break on composite materials right now, to your point of like flooding the part with water to do that, like a dip tank. Say you're using like a dip tank, or maybe you're spraying it down. You typically have to put that composite in an oven to dry it out. I think David actually was talking a little bit about kind of, absorption of moisture or water in the materials. And that can be a couple hours. When you're putting a couple spots of water on that composite surface, you don't have to do that anymore. So you can literally save hours of time and energy and huge energy cost by not doing a water break check. But what you want to set up is the right sampling frequency in the right locations, so you've got confidence that the part is in good shape.
On that same note, with water break testing, oftentimes on composites anyway, rather than just wiping the surface again, you're generally drying it, and that time to dry can also have a knockdown. I had a customer that was using a gas-fired oven to dry in, and we found that the contact angle went way up on that surface after that drying operation, and that was part of their issue. So it was then decided not to do the water break test. So these kinds of things can be, it could be something that's not obvious, like the oven itself that they were drying in, and it wasn't covered or put into some sort of bag or vacuum bag or anything like that. So it was a problematic issue. The next question we have up here today, let's see. We have one here that says, our company repair parts with plasma spray application, and we do have some peeling material issues. Do you have experience with plasma applications? I would say yes.
Yeah. Yes. Yeah, we do. And plasma spray is a little bit different than the plasma I've been referencing in the presentation, but short answer is yes. We're just actually working on, I don't even know how to describe this. We'll just call it a turbocharger. Working on some turbochargers that have plasma spray applied for that exact type of work. So, Victor, I think I see your question there. Happy to talk afterwards, right? Maybe there's something we can help with.
Okay, one more question, and then we've got to wrap it up. Feel free to contact Lucas after the event as well if you have any further questions. Are there plans to utilize other test liquids in the SA cartridges?
Yep. So we've done testing with various solvents of different polarities to try to get an understanding of what matters. And right now, other than changing like the surface tension to be able to measure something ultra hydrophobic, we really haven't found other liquids that we found to be really that useful. So right now, still water seems to be the most sensitive for the widest range of applications for what we're trying to do. There are cases where you want to use maybe other liquids if I'm doing some different development of a liquid coating or something like that. But that's not really what we're doing right now. Like for us, it's very much applied. It's like How do we get data when we're trying to build the component, when we're trying to maintain that program, when we're trying to solve that problem? How do we create the most useful, most generalized setup? And water still seems to be quite good for that.
Excellent. Okay, we're at the end of our time period. If you do have any questions, please feel free to contact Lucas. He will answer your questions and maybe help you out with your process. SME will be posting a link to the recording. Carl, can you provide us details?
Yeah, great. Thank you. Thank you, Lou, and thank you, Lucas, for your insights into the challenges and opportunities associated with surface inspection. We appreciate your time spending with the community and with us this afternoon. And of course, special thank you to all of our attendees who participated this afternoon. And we hope you found this webinar to be useful and helpful. This webinar, as Lou had mentioned, will be recorded, has been recorded, and we'll get it up on our Aerodef manufacturing website within about 24 hours. And as you see the slide that just popped up, be sure to block your calendar for Aerodef manufacturing, which is November 7th through the 9th, 2023. So we're still a little bit over a year away, but get that on your calendar. It's at the Long Beach Convention Center in Long Beach, California. So those of us who are in the Northwest would probably appreciate a nice California trip. Thanks again, everyone, for your time. Head to our Aerodef website, and the recording will be available in about 24 hours. Thank you, and we'll see you next month. Bye-bye.
Thank you all.
Thank you.